the next important constraint that we would talk about is the relationship between the real and imaginary parts of the loop gain, or equivalently the relationship between the magnitude and the phase plots of the open loop gain L in a Bode plot. Now the question that we want to ask is whether it is possible to independently design the magnitude characteristic and the phase characteristic of the loop gain, or equivalently is it possible to independently design the imaginary part and the real part of the loop gain. Well, this question is of obvious attraction and interest to us as engineers, because in terms of performance what we need to pay attention to is the magnitude characteristic. We need to make sure that the magnitude is high enough in the frequency ranges where we want to achieve robustness or disturbance rejection or tracking of a certain reference or something like that. So if we could independently engineer the magnitude characteristic and the phase characteristic, then we can first design the magnitude characteristic to satisfy whatever performance specifications have been given to us, and subsequently look at the phase characteristic, determine the phase margin, and if the phase margin is not adequate, then separately shape the phase characteristic in order to achieve whatever phase margin we desire. So therefore the problems of stability can be greatly minimized by adopting the systematic procedure for control design, provided we can independently realize the real and imaginary parts of the loop gain, or equivalently the magnitude and the phase of the loop gain. But what we will see in this discussion is that unfortunately this is not possible. The magnitude and the phase characteristics are intimately linked, and if you for instance specify the real part of the loop gain over the entire frequency range, the imaginary part of the loop gain also gets fixed over the entire frequency range and vice versa. So let us see how that can be arrived at. To do that, we would be applying Cauchy's theorem to a function f of s that has been given here. F of s is equal to L of s by s minus j omega naught, where L of s is our loop gain and this is a form a plus jb. In order to apply Cauchy's theorem to this particular function, we need to make sure that this function does not have singularities within the region where we are applying the theorem. Now if we were to adopt the same D-shaped contour that we took in the previous clip, then we would have a problem, because the point s is equal to j omega naught would be a point on the D-shaped contour, and hence it would become difficult for us to apply Cauchy's theorem. In order to avoid this uncomfortable situation, what is done is we shall distort the D-shaped contour that we saw in the that we have used in the past, in order to avoid the point s is equal to j omega naught, which is the point at which the singularity of this function f of s is located. So to do that, we choose a curve that is shown by this dotted contour here. So most of it is essentially the D-shaped contour that we have always considered when we have talked about stability and when we derived the relationship for conservation of sensitivity, dirt and so on. But there is a small kink that is introduced centered at the point j omega naught and of radius small r. So this small semicircular arc just avoids the point s is equal to j omega naught and hence excludes it from within the boundary of the contour C. So the rest of the contour C is a region where the function f of s does not have any singularities by assumption, because the loop gain L is assumed to be a minimum phase loop gain and all its poles and zeros are assumed to be located on the left half of the complex plane. So to apply Cauchy's theorem, we shall now divide up this contour into 4 segments. The first is the segment C1, which is essentially the imaginary axis all the way from minus infinity to a point that is very close to the point s is equal to j omega naught. The second is the contour C2, which is a tiny semicircular arc of radius small r, which just avoids this point s is equal to j omega naught. The third is the segment C3, which extends from s is equal to j omega naught all the way to plus infinity, and the fourth is the familiar D-shaped contour C4, whose radius capital R is tended to infinity and helps us to encompass the entire of the right half of the complex plane. So if we were to apply Cauchy's theorem to this particular contour, we would have that the contour integral over C of f of s would be equal to 0, which would mean that the sum of the integrals along C1, C2, C3 and C4 would be equal to 0. Now we shall evaluate each of these integrals separately and finally simplify the resulting algebraic expressions to ultimately arrive at a relationship between the real and imaginary parts of the loop gain. Since a lot of algebra is involved here, I am stating at the very outset that the goal of all the algebraic simplifications and solving of integrals that we would do in the subsequent 1 or 2 slides would be to ultimately obtain the relationship between the real and imaginary parts of the loop gain. So having stated that, let us now plunge into solving these integrals and undertaking the necessary algebra for the same. Let us first call these integrals I1, I2, I3 and I4, with I1 corresponding to the integral along the curve C1, I2 along the curve C2 and so on and so forth, and let us first try to solve the integral I4. The integral I4 is along the curve C4, and along the curve C4 we have that our complex number s would be of the form s is equal to r e power j phi, where r, capital R, is the radius of this big D shaped contour which is tended to infinity, and phi is the angle that a complex number on this D shaped contour makes with the real axis, and I am indicating here the angle phi. So for all points on the contour C4, we would have the complex number s to be of the form r e power j phi, and if we negotiate this contour in the clockwise sense as we have done in this schematic on the right, then the complex number s starts on the positive imaginary axis and traverses along this D shaped contour in a semicircular arc and finally ends in the negative imaginary axis. Hence we would have the angle phi going from plus pi by 2 to minus pi by 2. Since s is equal to r e power j phi, we would have that ds will be equal to j times r e power j phi d phi. So here we have the radius r to be a constant, and hence we would get this as the expression for ds. The second fact that we can exploit while solving the integral I4 is to note that since the loop gain is the product of the controller and the plant transfer functions, and each of the transfer functions, the controller and the plant, are both physical systems, we need to have the relative degree of each of these transfer functions to be at least equal to 1. Hence in the limit that s tends to infinity, or equivalently as capital R is tended to infinity, we can easily show that the loop gain L in the limit s tends to infinity would assume the form k by s power n, where the index n is greater than or equal to 2. We would have this index to be greater than or equal to 2 because L is a product of the controller and the plant, and each of them has to tend to 0 as k by s or k by s power alpha, where alpha is greater than 1, and hence the product of the two tends to 0 as k by s power n, where n is greater than or equal to 2. So if we exploit this fact along with the expression for ds along the contour C4, we would have the integral I4 to be limit r tends to infinity integral pi by 2 to minus pi by 2 L of s ds. So for ds I have substituted d of r e power j phi divided by s minus j omega naught. Now s minus j omega naught represents r prime e power j theta prime, where r prime is the phasor starting from s is equal to j omega naught and ending at the point s, and theta prime is the angle that this phasor makes with respect to the real axis. So this angle here is theta prime. Now once again, since we have the loop gain L on this contour C4 to be of the form k by s power n, or in other words k by r e power j phi to the power n, where n is greater than or equal to 2. Following the exact same arguments that we had in the previous clip, we can show easily that in the limit r tends to infinity, we would have this integral I4 going to 0. So of the 4 integrals that we have to simplify, one of them has a fairly simple expression, namely that I4 is equal to 0 for the particular function f of s that we have chosen. Let us now focus on the integral I2, and for the integral I2 we would be computing this integral along the curve C2, and along the curve C2 is essentially this tiny semicircular arc centered at the point s is equal to j omega naught and of radius small r, where the small r is vanishingly small, it is tended to 0. So any complex number s along this contour C2 would have the form s is equal to j omega naught plus r e power j alpha, where alpha is the angle made by a complex number s on this contour C2 with respect to the real axis. So I am marking the angle alpha in this graph here. So as you see, if we traverse the entire contour C in the clockwise sense, then the angle alpha changes from minus pi by 2 to pi by 2 as the complex number moves along the contour C2. So since s is of this form and omega naught is a constant, we would have ds to be equal to j times small r e power j alpha d alpha. So once again small r is also a constant, so we do not need to differentiate the variable small r. So the integral I2 therefore becomes I2 is equal to integral over C2 f of s ds, and that is equal to limit small r tended to 0 integral from minus pi by 2 to pi by 2 L of s d of r e power j alpha divided by r e power j alpha. So we get d of r e power j alpha because ds essentially will become equal to d of r e power j alpha since j omega naught is a constant, and in the denominator we get r e power j alpha because in the denominator of the function f of s we have f of s to be equal to L of s divided by s minus j omega naught, and if you notice along the curve C2 we have s to be equal to j omega naught plus r e power j alpha, which implies that s minus j omega naught will essentially simply be equal to r e power j alpha. So that is the reason that because we have the term s minus j omega naught in the denominator of the integrand, we will have the term r e power j alpha appearing in the denominator of the integrand. Now since this contour C2 is of vanishingly small radius and is situated very close to the point s is equal to j omega naught, for all practical purposes the loop gain L of s does not change within this contour C2, and therefore L of s can be assumed to be a constant along the contour C2 equal to L of j omega naught. So this term L of s can be replaced by L of j omega naught simply because the radius r is tended to 0. So we are only considering points that are extremely close to the point s is equal to j omega naught, and for all those points the loop gain L of s will be extremely close to L of j omega naught. So we can replace L of s by L of j omega naught. So if we do that, then L of j omega naught is a constant and it can be removed out of the integral, and all we would be left to evaluate is the integral minus pi by 2 to pi by 2 of d of r e power j alpha divided by r e power j alpha, and this can be shown to be equal to minus j times pi. Hence when we combine that with the term L of j omega naught, we would get the expression for I2 to be equal to minus j times pi times L of j omega naught. So we are now done solving I4, found it to be equal to 0, we just solved I2 and found it to be equal to minus j pi of L of j omega naught. What we are left with are integrals I1 and I3. Let us take these two integrals up next. So I1 plus I3, which is what we need to evaluate, is essentially integral along the contour C1 of f of s plus the integral along the contour C3 of f of s, and that is essentially given by this expression because f of s is L of s by s minus j omega naught. Now if you notice in the previous slide, the curve C1 and C3 are essentially coincident with the imaginary axis of our complex plane. Therefore along these curves we would have s to be of the form s is equal to j omega. So making that substitution, so that ds in turn will be equal to j times d omega, and the curve C1 starts at minus j infinity and ends at a point that is just below the point s is equal to j omega naught, and hence we would have the limits of the first integral, namely the integral over C1 of L of s by s minus j omega naught ds, to start from minus j times capital R, where capital R is tended to infinity, and stop at j times omega naught minus small r, which is the extent to which the curve C1 extends. So the integrand will be L of j omega by j omega minus j omega naught, because along this curve s is going to be equal to j omega, and we have replaced ds by j d omega. So this first integral within the bracket essentially represents integral over C1 of f of s ds. The second integral represents the integral over the curve C3. The curve C3 starts at a point along the imaginary axis that is just a little bit above the point s is equal to j omega naught. In fact, the distance of the point at which it starts from the point s is equal to j omega naught will be small r. So the point at which it starts will be j times omega naught plus r, that is the lower limit of the integral for when we are trying to do the integration along the curve C3, and it extends all the way to plus j infinity, or in other words plus j capital R, where capital R is tended to infinity, and the integrand once again is the same, L of j omega by j omega minus j omega naught, and ds once again gets replaced by j d omega. So this is the sum of the integrals I1 and I3. Now we know that L is of the form a plus jb, and if you substitute that in this expression, we would have that this entire integral, the sum of I1 and I3, can be written out as integral from minus infinity to infinity a of omega plus j times b of omega by omega minus omega naught d omega. That is because the first integral starts at minus j infinity or minus j capital R, where R is tended to infinity, stops just a little bit before j omega naught, and the second integral starts just a little bit above j omega naught and goes all the way to plus j infinity or plus j capital R, where R is tended to infinity. So if you combine these two, since the distance at which the first integral ends from the point s is equal to j omega naught and where the second integral begins from the point s is equal to j omega naught is small r, which is tended to 0, we can combine these two integrals and write out the integral that we have shown here. The limits will go from minus infinity to plus infinity, a of omega plus j b of omega divided by omega minus omega naught d omega. This is essentially a simplified version of the integral that we have written out here. And from the previous slide, we know that the other integral, namely the integral I2, will be equal to minus j pi times L of j omega naught, and that is going to be equal to 0. Now we know that L of j omega naught will essentially be equal to a of j omega naught plus j times b of j omega naught. So the integral here, which I have shown, which I am underlining now, has a real part and an imaginary part, and the expression minus j pi L of j omega naught also has a real part and an imaginary part. So if we compute minus j pi times L of j omega naught, we would have that to be equal to minus j pi a of j omega naught plus pi b of j omega naught. Hence if we equate the real part of the integral plus the real part of this term minus j pi L of j omega naught to be equal to 0 and the imaginary parts correspondingly to be equal to 0, we end up with these two expressions here. So we would have minus pi times b of omega naught is equal to integral minus infinity to infinity a of omega d omega by omega naught minus omega, while pi times a of omega naught will be equal to integral minus infinity to infinity b of omega d omega by omega naught minus omega. So we got these two expressions by separately equating the real part and the imaginary part of the equation that we have here to 0. Now this equation tells an important story. What is b of omega naught? B of omega naught essentially represents the imaginary part of the complex number L of j omega at the frequency omega naught. What is a omega? A omega represents the real part of the loop gain, and let us say that has been specified over the entire frequency range, namely omega going from 0 to infinity, then A of omega is known very well. So, we see that if we specify A of omega, we are automatically therefore specifying the numerical value of B of omega naught via this first equation. Conversely, if we are specifying the imaginary part of the loop gain, which is B of omega over the entire frequency range, omega going from 0 to infinity, then the second equation reveals that this specified B of omega over the entire frequency range can be used in combination with this particular integral on the right hand side to compute A of omega naught, or in other words the real part of the loop gain at any particular frequency omega naught. The trouble with the integrals on the right hand side, however, is that the frequency varies from minus infinity to infinity rather than from 0 to infinity. So, we can simplify this expression by taking one additional step through which we can replace the limits of the integral from minus infinity to infinity by 0 to infinity. So, let us undertake this next step for the sake of this last step of simplification. To do this, we apply the exact same steps that we have undertaken so far to the function f of s is equal to L of s by s plus j omega naught, which is basically a plus jb by s plus j omega naught. Please recall that 2 slides back we chose to apply Cauchy's theorem to the function f of s is equal to L by s minus j omega naught. Here we are choosing to apply it to f is equal to L by s plus j omega naught. Now, in order to apply Cauchy's theorem to this particular function, we have to introduce a tiny semicircular kink to the contour C at the location s is equal to minus j omega naught in order to avoid the singularity of this function at that particular point. Otherwise, if we follow the exact same steps as what we did in the previous 2 slides, then we would get a very similar expression that relates B of minus omega naught to A of omega and A of minus omega naught to B of omega. So, for negative frequencies omega, the real part and the imaginary parts of the loop gain are related as given by these 2 equations. Now, there is one last step that will allow us to replace the limits of these integrals in a manner that we had planned to do, namely to get the lower limit of both these integrals to be 0 rather than minus infinity. To do that, we notice that since the loop gain represents the transfer function of some physical system, we would have the real part of the loop gain be an even function of frequency, or in other words we would have A of minus omega to be equal to A of omega, and the imaginary part of the loop gain would be an odd function of frequency, or in other words B of minus omega would be equal to minus B of omega. So, by exploiting the fact that if L of omega is equal to A of omega plus j times B of omega, we would have A of omega as a even function of frequency and B of omega as an odd function of frequency. We can use the expression that we have in this slide along with the expression that we had in the previous slide, combine them, take the linear combination suitably and show that A of omega naught can be written out as 2 by pi times integral 0 to infinity omega times B of omega d omega by omega naught square minus omega square, and B of omega naught is equal to minus 2 omega naught by pi times integral 0 to infinity A of omega d omega by omega naught square minus omega square. So, this expression is directly the result of using the 2 equations that we have in this slide along with 2 similar equations that we had in the previous slide, combining them appropriately. The exact steps that will allow us to get to the final expression from these 2 expressions has been given in the lecture notes. But what is important is what these 2 equations tell us. What they tell us is that there is absolutely no freedom available to us in picking the imaginary part of a loop gain, which is essentially going to be B of omega naught, if we have specified its real part, namely A of omega over the entire frequency range. So, if A of omega is specified everywhere, then all we can do is compute this integral that we have on the right hand side to get b of omega naught. Likewise, if we have specified the imaginary part of the complex number, namely b of omega over the entire frequency range, then we have no flexibility whatsoever left in determining the real part of this complex number at any particular frequency omega naught. So, to determine its real part, we just have to compute the first integral that is shown in this equation. So, we would get a of omega naught to simply be equal to 2 by pi times integral from 0 to infinity omega times b by omega naught square minus omega square d omega, and that gives us a of omega naught. So, this is a real big constraint on us control engineers, because it tells us that we cannot independently determine the real and imaginary parts of the loop gain, or equivalently the magnitude and the phase of the loop gain. So, if we specify one over the entire frequency range, the other gets automatically specified at every single frequency omega naught, and that is given by the expressions that is shown here. But the relationship between the magnitude and the phase is far more intimate than what is apparent from these two equations. The intimacy of the relationship between the magnitude and the phase was revealed by H.W. Bode, who took these expressions further, made some simplifications and reorganizations to reveal how closely the phase characteristics get determined by the magnitude characteristics in the neighborhood of a frequency omega naught. So, what we shall do next is follow along H.W. Bode's footsteps, and starting from these two expressions, we shall see how the magnitude and the phase characteristics in a Bode plot are related. To do that, let us first choose to apply Cauchy's theorem, this time to the function f of s is equal to ln of L of s divided by s plus or minus j omega naught, or in other words, since ln of L of s is going to be given by ln of magnitude of L of s plus j times angle of L of s, we would have f of s to be equal to ln of magnitude of L plus j times angle of L divided by s plus or minus j omega naught. So, we first apply it to the case when we have s plus j omega naught in the denominator, and subsequently to the case where you have s minus j omega naught in the denominator, and exactly as we did in the previous slides, and then add the two, combine the two, and we would get the expression b of omega naught, where b is the angle of L and a is the ln of magnitude of L, to be equal to minus 2 omega naught by pi integral 0 to infinity a of omega d omega by omega naught square by minus omega square. So, this expression we borrowed from the previous slide, but we are applying it to the function f of s equal to a plus jb, but this time a does not represent the real part of L and b does not represent the imaginary part of L. Instead, a represents ln of the magnitude of L and b represents the phase of L or the angle of L, and that is because we have chosen our starting point to be that we would apply Cauchy's theorem to the function f of s is equal to ln of L divided by s plus or minus j omega naught, instead of directly L divided by s plus or minus j omega naught. Now that we have this particular expression, let us rearrange it a little bit. So, the term omega naught in the numerator was taken to the denominator, so that, and the term minus 1 was also absorbed by the integrand, so that we would have b of omega naught to be equal to 2 by pi times integral 0 to infinity a of omega d omega, which is the same as what we had in the previous expression, divided by omega by omega naught minus omega naught by omega times omega. So, by simple manipulation and rearrangement, you can quickly see that the expression that we have here on the right side is identical in every sense to the expression that we have beside it on the left hand side. It is just a rearrangement, and this rearrangement has been made to help us take the next step. In the next step, what we would do is define a new variable u. So, we have called u as ln omega minus ln omega naught, and we shall write out this integral in terms of u. So, the moment you define u to be equal to ln omega minus ln omega naught, you notice that u is equal to ln of omega by omega naught, or in other words omega by omega naught will be equal to e to the power u. Likewise omega naught by omega will be equal to e to the power minus u. Finally we would also have t omega by omega to be equal to du, since ln of omega naught is a constant, and hence d of ln of omega naught will be equal to 0. So by noting that the term d omega by omega in the rightmost integral here is equal to du, and omega by omega naught is equal to e power u, and omega naught by omega is equal to e power minus u, we can write that b of omega naught is equal to 2 by pi integral minus infinity to infinity a of u du by e power u minus e power minus u. Kindly note that the limits of integration have also changed as a consequence of the change of variables. Earlier we had omega, and omega was going from 0 to infinity. Now when we write out the same integral in terms of u, which is ln of omega, we would have ln of 0 to be minus infinity, and hence the lower limit of this integral becomes minus infinity, and ln of plus infinity still remains infinity, hence the upper limit still remains plus infinity. We would therefore have b of omega naught to be equal to 2 by pi integral minus infinity to infinity a of u du by e power u minus e power minus u. Now you notice that e power u minus e power minus u divided by 2 is essentially equal to sine hyperbolic of u. So by noting this particular definition of sine hyperbolic of a variable, we can write out the same integral here as 1 by pi times integral minus infinity to infinity a of u du divided by sine hyperbolic of u. Next what we do is undertake integration by parts to simplify this particular integral. This has not been done by me in this particular slide, but it is in the lecture notes and you can refer to it at some later point. What we can show is that this integral here, the rightmost integral that I am currently underlining, can essentially be simplified by using integration by parts to this particular expression here, namely that b of omega naught, which is essentially equal to angle of L, is equal to 1 by pi times dA by du, where A is ln of magnitude of L, times ln of cotangent hyperbolic of magnitude of u by 2 du. So this is the relationship between the angle of the loop gain and the magnitude of the loop gain. So the angle of the loop gain is equal to 1 by pi times this integral of some slope of the loop gain, namely d ln of magnitude of L divided by du, weighted by this function ln of cotangent hyperbolic of magnitude of u by 2 du. Now if you examine this relationship, it is not easy to tell exactly what it is about this so called simplification that sheds any further light on the relationship between the magnitude and the phase characteristics of the Bode plot, or the angle and the magnitude of the loop gain in a Bode plot. That is because we do not know exactly how this particular function ln of cotangent hyperbolic magnitude of u by 2 looks like. The moment we plot this function, things will start to become immediately a bit more clear. So if one were to plot this function ln of cotangent hyperbolic magnitude of u by 2, it looks something like this. So as u tends to infinity, it tends to 0, as u tends to minus infinity, once again it tends to 0, and at u equal to 0 the function tends to infinity. So this function is of infinite magnitude in the neighborhood of u equal to 0, and it tends to 0 as we move farther away and as u is tended to infinity. Now we might wonder, what function does this particular function resemble? A moment's thought might lead us to suspect that perhaps this function ln of cotangent hyperbolic of magnitude of u by 2 looks somewhat like a delta function, namely delta of u, because if I were to draw a delta function also has infinite magnitude in the neighborhood of u equal to 0 and quickly goes to 0 outside of u equal to 0. So, you would imagine therefore that perhaps ln cotangent hyperbolic u by 2 is actually a delta function, but the bad news is this function is not exactly a delta function. So, a delta function's definition was provided in the very beginning of this course, and if we apply that definition we will discover that this particular function is not really a delta function, but it can be approximated as a delta function simply because it weighs the integrand, namely d of ln of magnitude of L by du significantly more in the neighborhood of u equal to 0 compared to other locations or other values of u. There is a second problem in equating or approximating ln of cotangent hyperbolic of magnitude of u by 2 with a delta function. That is because when we compute the area under the curve for a delta function, or when we compute integral minus infinity to infinity delta of u du, by definition we should get that area to be equal to 1. However, when we compute the integral ln of cotangent hyperbolic of magnitude of u by 2 du, we do not get that area to be equal to 1. Instead, you get it to be equal to pi square by 2. Hence, this term ln cotangent hyperbolic u by 2 is not only not a delta function, but also that the area under its curve is not 1, it is actually equal to pi square by 2. However, in order to simplify analysis and given the fact that it weighs the integrand significantly more around u equal to 0, we can approximate ln cotangent hyperbolic u by 2 as pi square by 2 times delta of u approximately, so that the area under the curve for the term on the right hand side, namely pi square by 2 times delta of u, will also be equal to pi square by 2, and this term will end up weighing the integrand significantly more near u equal to 0. So, by approximating this function ln of cotangent hyperbolic magnitude of u by 2 as approximately being equal to pi square by 2 times delta of u, we would have the relationship between the phase of L and the magnitude of L to approximately be given by b of omega naught is approximately equal to 1 by pi dA by du pi square by 2 delta of u du, where I have replaced ln of cotangent hyperbolic u by 2 with pi square by 2 times delta of u, and b of omega naught essentially represents the angle L as based on the definition that we have laid out at the beginning of the slide here, and d of ln of magnitude of L by du is essentially dA by du, because by definition A is ln of magnitude of L. Hence, dA by du essentially represents this term here. So, the term L of omega naught has been reproduced in this equation. The term d of ln of magnitude of L by du has been reproduced again here, just that we have renamed the same variable as A, and the term ln of cotangent hyperbolic magnitude of u by 2 has been approximated as pi square by 2 times delta of u. So, when we simplify this particular integral by noting that we have a delta function within the integral and we remove the term pi square by 2 out of the integration, we would get that b of omega naught is going to be equal to pi by 2 times dA by du evaluated at u equal to 0. This we get because of the presence of the term delta of u inside the integration. Now, if we once again substitute what A, the variable capital A stands for, and what the variable capital B stands for, we would get this very interesting expression, namely that the angle of j omega naught, which is essentially b of omega naught, is approximately equal to pi by 2 times d of dA by du essentially represents d of ln of magnitude of L, because by definition A is equal to ln of magnitude of L, by du, and u represents ln of omega. Hence, we would have the angle of L at j omega naught to be approximately equal to pi by 2 times d of ln of magnitude of L by d of ln of omega at the frequency omega equal to omega naught. Now, since we have drawn the Bode plots for quite some time in this lecture series and perhaps also before this, we will immediately recognize that in a Bode plot the y axis is proportional to ln of magnitude of L. It is actually equal to 20 times log to the base 10 of magnitude of L, which is proportional to ln of magnitude of L, and the x axis is essentially log to the base 10 of omega, which is essentially again proportional to ln of omega. So, what this expression tells us therefore is that the angle of L at any particular frequency omega naught is simply equal to approximately the slope of the magnitude characteristic in a Bode plot at the frequency omega naught. So, if we have the Bode plot where we plot log of omega versus 20 log of magnitude of L, we let us say have a certain Bode plot for our open loop gain at any particular frequency omega naught. If we compute the slope of this curve, then that slope of that curve is proportional to the phase of the loop gain at that particular frequency. And what this in turn indicates to us is that it is not necessary for us to separately draw the magnitude and the phase characteristics of the loop gain. If you are given the magnitude characteristics, you can automatically derive the phase characteristics by using this approximate expression, and that is the power of this relationship between the magnitude and the phase that has been derived by H.W. Bode. So, is this really true? To check if this is really true, we can apply this expression to a few common transfer functions that we have come across and we tend to come across in practice, and see whether this relationship between the magnitude and the phase are really correct or not. So, I have chosen to first apply it to the loop gain L equal to 1 by s by alpha plus 1. This is a first order system, and for this system we can compute the magnitude of L at any frequency omega and then take its logarithm and take the derivative of log of magnitude of L with respect to log of omega, and show that after some algebraic simplification it becomes equal to minus omega naught by alpha the whole square divided by 1 plus omega naught by alpha the whole square, where omega naught is the frequency at which we are trying to evaluate the derivative d of ln of magnitude of L by d of ln of omega. So, this is evaluated at omega equal to omega naught. Hence, if Bode's gain phase relationship were to be true, we would have that the angle of L would be equal to pi by 2 times minus omega naught by alpha the square divided by 1 plus omega naught by alpha the whole square. So, what I have done on the right hand side is plotted the magnitude characteristics of the loop gain for some particular alpha. In this case I have chosen alpha to be equal to 1, and I have also plotted the actual phase of this loop gain, which is quite easy to derive because the angle of L actually is given by minus of tan inverse of omega naught by alpha at any particular frequency omega naught. So, the actual phase has been shown in blue colored solid curve here, and the approximate phase has been shown by the red dashed curve here, which is obtained by using the approximate gain phase relationship that we derived in the previous slide, namely that the angle of L is equal to pi by 2 times, approximately equal to pi by 2 times the derivative of ln of magnitude of L with respect to ln of omega. And what you see from the graph on the right hand side is that the two are quite close, and the maximum difference between the two which you can compute is going to be about 6 degrees, which is not a bad number, and as control designers we can live with this small difference between the actual phase and the approximate phase. And the benefit we would get from that is that we can just rely on the magnitude characteristics in order to perform our control design, because by taking the derivative of the magnitude characteristics we can estimate the approximate phase characteristics of the loop gain, provided this loop gain is a minimum phase loop gain, and from that work out the other stability specifications such as the phase margin and so on and so forth. Now if you take a more general loop gain, namely L is equal to k times S by Z1 plus 1 times S by Z2 plus 1 and so on and so forth up to S by Zm plus 1. Let us assume you have m zeros Z1 to Zm and n poles for our open loop system P1 to Pn, so that the denominator polynomial can be factorized as S by P1 plus 1 times S by P2 plus 1 and so on and so forth up to S by Pn plus 1. We can show with some algebraic manipulation that d of ln of magnitude of L by d of ln of omega is given by this particular expression within the brackets here, namely summation I going from 1 to m omega naught by Zi the whole square divided by 1 plus omega naught by Zi the whole square minus summation j going from 1 to n omega naught by Pj the whole square divided by 1 plus omega naught by Pj the whole square. So this entire sum multiplied with pi by 2 will approximately give us the phase of L at any particular frequency omega naught. To verify whether this is correct or not, I have taken once again a specific numerical example. L of S is equal to 1 by S times S plus 1 times S plus 2, and the top graph plots the magnitude characteristics of this loop gain. Since we have an integrator, initially we have a minus 20 dB per decade roll off, and at 1 radian per second, which is its first corner frequency, the roll off will increase to minus 40 dB per decade, and at the second corner frequency, which is at 2 radian per second, there will be an additional roll off introduced by the second by the pole at S is equal to minus 2, and so the ultimate roll off will be minus 60 dB per decade. And for this particular magnitude characteristics, we can compute the exact phase characteristics because we know the 3 terms that make up this loop gain. So the exact phase at any particular frequency omega naught is given by angle of L of j omega naught is equal to minus pi by 2, which arises from the integrator 1 by S that we have, and then minus tan inverse of omega naught by 1 because of the pole at S is equal to minus 1 minus tan inverse of omega naught by 2 because of the other pole at S is equal to minus 2. So this is going to be the exact phase. The approximate phase can be computed by using this expression which I am now highlighting between the brackets, and the second graph here compares the approximate phase and the actual phase. You see that the actual phase is shown in blue solid curve and the approximate phase is shown by once again the red dashed curve, and it is evident from this that the two are very nearly identical to one another. It is only at some particular frequencies that there is a difference, but if you zoom in and look at the difference, it is going to be quite small, on the order of a few degrees or at most 10 degrees to 15 degrees, and this difference is small enough for us control engineers to live with. So the importance of the second half of our discussion in this clip is that not only is the phase characteristic completely determined if you are given the magnitude characteristic of the open loop gain, but in fact the phase characteristic is determined predominantly by the slope of the magnitude characteristic in a Bode plot in the neighborhood of the frequency at which we are determining the phase characteristic. So although the magnitude characteristic at other frequencies, or in particular the slope of the magnitude characteristic at other frequencies also affect the phase at a particular frequency omega naught, that contribution is rather small. What is dominant is the slope of the magnitude characteristic in a Bode plot, or in other words the slope of the ln of magnitude of L versus ln of omega at a particular frequency omega naught is what determines the phase characteristics at the same frequency omega naught. Thank you.